Hello and welcome everyone to this webinar on CFD in thermal management. My name is Advait Gupta and I am the CEO of Paanduv Applications Private Limited. I am a CFD engineer and an AI engineer by profession, and I will be delivering the webinar for today. We have over 1400 registrations for this currently hot topic, and I'm really looking forward to interacting in the chat panel as I progress through the webinar. We'll start directly with the electric vehicles, which is a very hot topic these days due to all the good and the bad news that we are hearing. And we will focus on two case studies, one on battery and one on fuel cell. Then we will discuss about thermal power plants and chemical industries, not necessarily the thermal power plant modeling itself, but the boiling aspect of it. Then we'll move on to clean energy, especially the nacelle design of a wind turbine and optimizing a nacelle. Then we'll move on to data center modeling, or the HVAC of a data center, cooling or air conditioning of a data center, and specifically we'll focus on underwater data centers, which are currently deployed by some of the big companies that we are aware of, including Microsoft. Then we look into some more of a traditional HVAC systems, heating, ventilation, and air conditioning for a car, for a vehicle. Before we proceed to the case studies, what does thermal management mean? So if I were to put it in simple words, it's the increase in temperature of a system that causes reduced efficiency and performance or reduced longevity. Now, this increase in temperature might in itself not be a problem, but sometimes non-uniformity in temperature distribution over a system might result in similar sort of inefficiencies and performance issues. Coming to computational fluid dynamics, or more popularly known as CFD, or a smaller subset of a larger computational modeling world, it can really help us understand and make our thermal based systems more efficient. For example, CFD can help us to understand our current existing process, and using that information about the process, we can develop more optimized and better performing systems. We can understand how heat is transferred between fluids and solids. Different modes of heat transfer, such as conduction, convection, radiation, and phase change, can be captured. And using all this information, design and geometry optimizations are possible. Once design and geometry optimization is done, you can use that to deploy to real-time scenarios based on the right input scenarios, such as charging and discharging curves for an electric vehicle. Within the domain of CFD, there's a methodology called conjugate heat transfer, or more commonly known as CHT, that solves a lot of the physics, or especially the thermal physics that happens between solids and the fluids in a thermal system. And all this is to say that it is a wise idea to model before manufacturing, and we will elaborate a little bit more about that in the upcoming slides. Yeah. A quick note on conjugate heat transfer. Like I said earlier, it is a methodology within the domain of numerical modeling that assists in capturing heat transfer between solids and fluids. And as far as the phase change is concerned, it can be a phase change from solid to liquid, liquid to gas, and vice versa. So you can go all the way from solid to liquid, and you can also go all the way from gas to solid. In short, a CFD in thermal management captures a lot of physics, including multi-phase, conduction, buoyancy effects, convection, radiation, pressure velocity coupling, solid liquid interface modeling, porosity capturing, turbulence capturing, and at the same time it captures the geometric complexity of a system. Now many a times these systems are very complicated and they have very intricate parts inside them, so it becomes important that all that geometric complexity is captured along with the right meshing strategy. The case studies that we'll be looking today, some of them are done for external people and some of them are done by Paanduv internally. to understand the CFD and the applicability of CFD to some of these industries. The first case study we'll be looking at is the battery or a battery pack, typically used in electric vehicles these days, followed by a case study on fuel cell, third boiling or boiling with bubble dynamics. Then we look at a nacelle thermal management for a wind turbine. Then we look at underwater data center. And lastly, we look at the heating, ventilation, and air conditioning of a car system. Right. So let's get started with the battery. And yeah, so battery is basically the heart of an electric vehicle. This is where you store the energy, and it is of paramount importance that these batteries operate in an efficient manner without degrading the performance of your vehicle. And there are a lot of aspects surrounding how you can maintain the performance and efficiency of a battery based electric vehicle. We'll start off with some of the statistics as to why electric vehicles are important and why CFD in electric vehicles are more important. So starting with the electric vehicles itself, the global sales of plug-in electric vehicles has doubled up, 98% increase from 2020 to 2021. Talking about India in itself, around more than 100,000 units are sold since 2019, and most of them are two-wheelers and three-wheelers, and that is not a surprise given the developing economical nature of the country. And for those of you who are from India, the biggest chunk of this electric vehicles is currently sold in Uttar Pradesh. Now, how is CFD relevant in this current explosion of electric vehicle market? Now, CFD in itself is growing at a rate of around 9% per year, a steady growth of 9%, which is a healthy rate. Out of the entire CFD market, around 35% market is originating from the APAC countries, which is Asia Pacific region. That includes India, China, Australia, New Zealand, and some of the other Southeast Pacific countries. Okay, it is estimated that one of the biggest drivers of CFD in the upcoming years is going to be the high adoption of electric vehicles in the market. So this is how CFD is very and directly relevant to electric vehicle market. Now, going back to the point of modeling before manufacturing, there are flaws in the system currently. I mean, this photo has become very popular in the news. This is a burning two-wheeler or a scooty, and it harms everyone in the process. I mean, there seems to be a rush in releasing premature technology to the market. Demand is very high. Manufacturers probably have not done enough computational modeling of their battery systems, and they have released the product to the market, and this is what is happening. So on the manufacturer side, you are losing face, right? You are basically, your licenses might be at stake, your reputation might be at stake, and from the customer side, it is directly costing the customer money, and even more importantly, the safety of the customer is at stake. So we can use CFD for reliability and CFD for safety. You have to do it if you want these two things to be 100% addressed, because you're dealing with humans here, right? So a robust electric vehicle requires optimization around these three parameters: the material, the design, and the dynamic system characteristics. So what material will you use in your battery packs? What should be the design of your battery pack for best thermal management, and how the dynamic system characteristics such as charging rate and the discharging rate are incorporated during the design of this electric vehicle. Okay. Another important aspect as to why eventually a two-wheeler is set on fire or a battery pack is set on fire is this term called thermal runaway reaction. Now, batteries operate or perform the best at the room temperature, and even there is some leeway there, they can operate up to 45 degrees Celsius as well. But as you start approaching a temperature of 90 degrees Celsius, things start becoming bad. Your solid electrolyte interface starts decomposing, and by the time you have reached 130 degrees Celsius, you start seeing internal short circuiting, and at 200 degrees Celsius it becomes a one-way chain reaction where fire to the battery becomes inevitable. right? Now, some of the battery cooling systems that are available in the market and successfully deployed are shown on this slide. The first mechanism is air cooling, currently deployed by Toyota Prius and Nissan Leaf. It's simple to use, requires more energy. However, it is typically more useful for slow charging and discharging rates. Liquid cooling, uh, patented by Tesla, efficient due to high heat capacity of fluids, and it has a flexibility with the application. Right. The third one is fin cooling, which is a very traditional thermal management system typically used in our laptops, CPUs, and these type of devices. They can be used, but they add 40% weight, where and with such dynamic aerodynamic systems such as cars, this might not be the best way to go. Last one is phase changing material based cooling, where the material actually absorbs the heat and changes its phase rather than absorbing the heat and transferring it along to the nearby molecules. So this adds design complexity due to the volume change, but this is one of the methods that is currently in research and probably deployed by some of the manufacturers out there. Now there's a possibility to mix and match some of the features. You can have little bit of fin cooling, you can have little bit of phase change material, but all this is up for research and further thinking. So when it comes to CFD in battery, there is a lot of things going on, a lot of physics that is captured and shown on the screen here. But let's move on to the internal case study that we did at Paanduv. So this case study contains 59 cells, okay, arranged in multiple rows, where a cell in a particular row is placed diagonally between two cells in the preceding row. Okay, so you can look at these circular cells. It's a top view, so you see the 2D plane of the cells here, and the grid or the meshing grid is also visible. So you can see that the cells are also captured in this computational domain. It's not just the surface of the cell, but actually the volume of the cell, which is modeled in this simulation. Reference representative inlet fluid is air, and the reason is because air cooling is successfully deployed by some of the manufacturers, but we have also deployed and tested water. See, this is the beauty of using CFD. I mean, you can easily change the properties of the coolant that you want and see how the thermal management comes out using CFD. Right, so we try air and water, and just for the sake of it, we want to compare what changes. Right, the cell material and the cover material of construction is iron. Again, you can change the properties of this construction material very easily in a virtual environment, in a safe environment. Turbulence is on, fluid inlet velocity is set to 50 meter cube per second, followed by some values for inlet fluid temperature and the constant heat source. Right. So we'll look at two things here. We'll first look at the flow of coolant around the cells, okay, and then the second thing that we look at is the temperature evolution of the cells themselves, right? So the coolant flow, you can see the velocity vectors, they are moving from the left hand side, which is the big inlet, to the two outlets on the right hand side, and the coolant as expected is trying to move around the cells. The red area on these contours indicates higher temperature, which makes sense because near the outlet the temperature should be higher, as all the heat is collected from this battery pack and it's kind of moving towards the outlet, and the blue area indicates lower temperature. Now if I were to play this video, I will actually play this video, you can see a very quick evolution. If I take a slice, this is actually a 3D simulation. The fluid or the red and the black area is actually filled all the way to the bottom of the cells, but for the sake of clear visibility, we have only taken a slice of it, right? And you can see how the temperature evolves, and then the temperature stays higher near the outlet, and towards the inlet the temperature falls down more drastically. Okay, now looking at the evolution of the cell temperature itself, we cut three slices across three rows of cells, and we see that the temperature at the inside or towards the center of the cell is higher compared to the temperature on the outer of the cell, which makes sense because the coolant is in more contact with the outer surface of the cell, so the cooling is happening from the outside to the inside of the cell. And if I were to play this video here, you can see how the cells are cooling down with time. And this is a quick comparison between air and water cooled battery pack. You can see that the air cooled battery pack has some dead zones, higher temperatures. Water cooled battery pack is expected to have more uniform distribution of temperature and less extreme dead zone formation, right? And that's because water has higher heat capacity, so it can take in more heat and take it out of the battery pack. But water is not a practical solution because it has leakage issues. It can cause short circuiting due to its high electrical conductivity in the system. Typically not used, but it can easily be replaced in a virtual environment with some other coolant, perhaps glycol or some phase change material as well. Now, as far as the air cooled battery pack goes, this is good. This is deployed by some of the people, despite some of its properties which are not as preferable as water, but for slow discharging and charging rates, this is a sufficiently good coolant to be used in the battery packs. Okay. Now, some of these things that we have shown are under further development, and some of them are already concluded. But this is our idea of where we are going forward with this whole battery pack or EV modeling, which is fins optimization, transient cooling, forced convection, natural convection, cooling jacket systems, cold plate systems, dynamic charging, slow and fast cooling, and then lastly, which is very important, is electric motor thermal management as well. Okay, moving on to the second topic, which is fuel cells. Uh, this is an alternative form of clean energy, again very relevant in the context of electric vehicles. It does not require any charging. There's a direct conversion of your fuel to hydrogen, which is the actual fuel to direct conversion to hydrogen, which can be directly utilized to generate energy. There's no storage required. And one advantage that we have with this fuel cells over battery packs is the longevity, which is more in the case of fuel cells. However, there are some disadvantages as well, which are currently explored in academia, such as fuel cells. Hydrogen is a very light gas, and so it requires a lot of space to store the hydrogen itself, and creating a small system to accommodate for the entire unit might be difficult sometimes. Okay, so thermal management, how is that relevant with fuel cells, right? So increase in temperature happens due to the constant electrochemical reactions near catalyst layers. So this is a typical fuel cell. You have anode and cathode, as always, and then you have some porous membranes in between, where a transfer of protons is happening, and electrons are moving through a circuit, right? This is how the electricity is basically produced, right? So increase in temperature is caused due to constant electrochemical reactions. Okay, then this increase in temperature causes inefficient reactions due to loss of moisture. Okay, your current density is reduced because of this increase in temperature, and overall the efficiency of your fuel cell is reduced due to this non-uniform or high temperature. A lot of things are going on here again in terms of physics, but I want to especially highlight the porosity aspect that comes into play when we are talking about these fuel cells, and which is efficiently captured using CFD, right? So if you look at some of the simpler schematic of what we have tried to simulate in this case study, so it is a co-flow. Co-flow means two streams of two fluids, one stream of one fluid each, they are coming together and mixing with it. This is what co-flow means, and they're moving in the same same direction, right? So in this case, fuel is hydrogen and oxidizer is oxygen, and the reaction kinetics of hydrogen and oxygen are utilized or simulated as it is in the computational model. This is a high temperature fuel cell because the inlet temperature is equal to 1000 Kelvin. The porosity of cathode and anode is at 50%, and the porosity of cathode and anode functional layers is lower, which is only 25%. The inlet velocity for both fuel and oxidizer is at 1 meter per second, and there are 25 parallel channels of this the cathodes and anodes, and that will become more clear in the next slide. Okay, so these are the actual simulation results that we have generated. The anode functional layer is on top. Okay, the cathode functional layer is on bottom, and electrolyte layer, and there's more layers. That thin black layer that you see is in between, right? And then we have some of the results. So you can see that there are 25 channels. If you look at the bottom right image, there are 25 channels in parallel. You can see that the temperature is varying from 1300 to 1400 plus Kelvin, which is not good. This temperature maintenance should be managed and thermally controlled in a better manner. So this was a case study that basically incorporates porosity, reaction kinetics, flow dynamics, thermal conjugate heat transfer, thermal management, this, that, everything. And you can see that the size of the layers is also in microns. So this is effectively captured. Okay, so the current and the future work that we are looking on for is cooling solutions for fuel cells, modeling of separate components within the fuel cell, and geometric optimizations in the channels. For example, what shape of the channels do you want in series, in parallel, things like that. The next topic is boiling, and what you typically boiling is assisted by bubbles or bubble dynamics. So we will see how boiling and bubble dynamics are effectively captured by simulation work that we have done at Paanduv. Okay, so boiling processes are important. We see it every day in our kitchen, but at an industrial scale, they are important because you first generate heat by the process of combustion. That heat is then absorbed by water to change its phase and turn it into steam. That steam is then thrown at the turbines to generate electrical energy, right? So when this conversion of water to steam happens, a lot of boiling and bubble formation happens, and capturing that bubble dynamics is important for the effective conversion of water to steam, to maintain the structural integrity of your system, to understand how much mixing. Sometimes you want to reduce mixing, sometimes you want to enhance mixing. So what level of mixing is going on, and there are many things that are associated with bubble dynamics. That's a whole big field of computational fluid dynamics in itself. On the chemical reactors side of things, bubble columns, photocatalytic reactors, we are working a lot on that side right now. There seems to be a lot of demand on that front. And then continuous stirred tank reactors as usual. So these are the places where you'll see a lot of bubble dynamics happening. Again, when it comes to CFD in boiling, a lot of physics is happening. Population balance is one of the techniques that we use for creating bubbles, and understanding the bubble velocity, their rising rate, their impinging rate, coalescence of bubbles, splitting of bubbles, mixing of bubbles, things like that. So we use a technique called population balance here. The simulation details for this simplistic yet powerful simulation are follows. The solid temperature of a thin plate, so the gray plate on the bottom of this on this image is heated to 123 Kelvin. Initial temperature of water, which is in black color, is 333 Kelvin. So you can see that the water is going to heat up, and then bubbles will rise. Bubbles will rise from this thin plate. Again, thin plate. Turbulence is used. Now I want to highlight this is a four-phase system. You have a solid plate, you have water, you have vapor which is converted from water, and then you have air which is on top of the whole system, right? So this is a four-phase system. So what we did, we put the plate in a vertical manner and then in a horizontal manner, and we ran the simulation. You can see that the bubble formation and the velocity contours are very different for the two cases. There's a much cleaner and more enhanced bubble formation that is seen on the horizontal plate, and again, if you have some novel technology or some clean technology of designing reactors, you might need such CFD analysis in your system, and we will be able to do that for you. Okay, so ongoing and future explorations, like I said, photocatalytic water splitting and CO2 reduction, high temperature multi-phase reactions for both porous media and non-porous media, bubble column mixing, modeling and mixing in general. So what you have in this green top left image is a porous media behavior for a reactor. And then if I play this video here, hydrogen, oxygen and water. So you'll see water is split into hydrogen and oxygen, and then on the bottom right you have another case study with partial bubble formation where you can see some wake formation and the new components or the products are rising to the top of the water column. Okay. Moving on to nacelle. So what you see on the screen is a nacelle. Nacelle is basically a box where all your generator, your fluid coupling, your rotors, and your air ducts, everything is coupled. And this is basically the place which has to be managed in a very effective manner for thermally, because all your after your fan rotates, a lot of dynamics happens inside this nacelle area. If this is on fire, I mean these are very tall. These nacelles are placed at a very big, very huge height. It's just difficult to extinguish them once they are on fire. The fire may happen due to overheating and lightning strike. And air cooling, water cooling, dual phase cooling, and refrigeration are some of the methods uh, for uh, for minimizing these scenarios. Okay, again, the CFD for such systems is basically encompassing a lot of physics. Again, especially I want to highlight geometrical complexity and the meshing complexity that goes into simulating such systems, and you will be able to appreciate this more with the photo on this, with this video that you see the rotating part. It's the very complicated CAD file, and we have covered all the components of this. So we have used complex unstructured meshing for complex geometry. We have used heat sources. So a generator, fluid coupling, and gearbox are heat sources. Fans are used as pressure jumps. And then we have a heat exchanger which is porous in nature, and Darcy and Forsheimer law is used to simulate that. And so what we wanted to do in this case study, take an existing nacelle design with all its components in place and see if we can reduce the heating. So what was proposed is increase the fan speed by 20% and add an additional new duct with this conical sort of design under. This is not a pure conical cone, but this design somewhere between the FC fan and fluid coupling. Okay, so if you look at these results, the baseline results, which is before optimization and after design modifications, you can see that the temperature and velocity contours are different. So a huge amount of heat is carried away by this new duct, which is placed in outlet number 2. If you especially look at the velocity contour, you can see that new duct is taking away a lot of heat from the system. The conclusions are very straightforward. Fluid coupling was earlier heating up to 575 degrees Celsius, but now it is reduced to 562 degrees Celsius. Generator box was heating up to 151 degrees Celsius. Now it is at 144. Gearbox, not much of a difference, but yet 1 degree cooling, you never know. Right. A quick note on the post processing of the simulations that we do. This is not a CAD file. This is a real image. These are the real photos or real CFD results, and these are rendered in a photorealistic manner using ParaView. So we use ParaView for all our post processing. You can see the detail on this nacelle, and you can see the generator box, fluid coupling. They are super hot, and you can even see the reflection of this entire system on the background wall, and basically you can see the fins in great detail. So this is the detail at which we have actually simulated the system, and it would be a shame if we were not able to show you through a wise post processing as well. Okay. Moving on to the underwater data center. So if you recognize, this is a Microsoft logo on the data center. They deployed 2 data centers, one in 2015 and 2018 in the North Sea, and you can see that after deploying the data center, they're pulling it out for maintenance and analyzing the thermal data. So why are underwater data centers preferred? Because they are greener and faster. They provide high speed to the users because they can be located closer to the customer's location. They use fewer resources for efficient operations and cooling, and it's an overall greener approach for data center operations. Okay, So why should one move from land data center to underwater data center? For that, there's a term called power usage effectiveness, which is basically the energy required for cooling and ventilation per watt energy for a single computer, right? So land data centers are currently consuming 200 tetrawatt hour of electricity globally, which is 1% of the global electricity demand. And the power usage effectiveness is very high. It's not good. I mean, it should be around 1 or lower than 4 to 5 for sure. This results in 0.3% of global CO2 emissions. If you think about underwater data centers, they are 8 times more reliable than the data centers on land. They are 10 degrees colder than the land data centers. Their life expectancy increases because they are better cooled to double, and the power usage effectiveness is 1.07. So the operating conditions in which this Microsoft data centers are deployed, they are more than 100 feet below the North Sea. There are 864 racks of data servers inside this underwater data center, which are installed on 12 racks. It is filled with nitrogen gas, which is less corrosive than oxygen. And if you want to get a physical idea as to how big this data center is, it is around 12-meter long and 2.8 meters in diameter. So what we did, we took the specifications and details from this data center and we tried to create a case study out of it. What you see on the left hand side is a real image of the data center. In the back side of the image, you see the circular or a cylindrical pod inside which the entire rack of data center will be pushed. On the right hand side, you have the CFD results. Remember, these are not CAD results. You don't see the CAD. This is not the CAD file that you're seeing. You're seeing the actual CFD results rendered in a very photorealistic manner. Okay, so this is what you see in the post processing. And another view here, if you remove the cylindrical pod and just focus on the internals, you have a heat exchanger system which contains water. Then you have racks of servers, and then so the heat exchanger is between the rack of servers and the outer fan system. Also, all these circular things, they basically pull air from the hot air from the data center and then throw them outwards. Okay. So some of the simulation details: outer temperature of the wall is at 287 Kelvin. Water inlet temperature is also at 287 Kelvin. Material of construction is copper. Conduction in metals is allowed. Convection at liquid solid interface is allowed. Convection in liquid is allowed. And forced convection of nitrogen in the pressure vessel is also allowed. Right. And I want to highlight on the meshing complexity of the system. This is just very complex, and appropriate meshing is used. So inside the heat exchanger with narrow tubes and channels, much refined mesh is used compared to the outer and more bigger parts of the data center. Right. So again, we'll focus on two aspects: one, the flow, and the second is temperature. So let's look at the flow dynamics here. You can see on the right hand side how the velocity distribution is happening. There's a lot of buoyancy happening, convection happening. So the flow, so the fans are pushing, throwing the air out, the hot air out away from the servers. That some of that air rises up, some of that air cools down, drops down again, and recirculates because of the cylindrical nature of the of this data center. And then if you look at the temperature evolution, you'll see that towards the sides or the outer sides of the data centers, they are more cool compared to the central part where there seems to be a dead zone for temperatures. And that makes sense because the edges of the data center are more in contact with the cool nitrogen compared to some of the central parts where the the convection might not be as efficient, and the forced convection might not be as efficient as it would be on the outside. Right. So we successfully captured the geometric complexity of this system, captured heat transfer, turbulent flows, solid liquid interfaces were defined, and appropriate boundary conditions were applied, the realistic ones, and we were able to achieve low cost and robust modeling for this system as well. So moving on to the last case study for today, is a traditional car heating, ventilation, and air conditioning system. So why do we require heating, ventilation, and air conditioning? I mean, Indians don't need to be explained that, but It basically controls heating, controls humidity, and maintains temperature so that it is comfortable to all the passengers and driver inside the car. Some of the causes of the heat are solar radiation and the engine heat itself, and higher temperature of the outside air. Um, so heat absorption, how much heat will be absorbed by the car, depends on many things like automobile insulation, position of sun, like what time of the day are you traveling, variation of light and shadow, vehicle class, vehicle color, tinted glass, vehicle speed, wind direction, and velocity. Okay, so this is a simple case study. We'll show a more complicated case study after this, but this is a simple case study of two stacks, two rows of seats of a standard Maruti car, uh, three seats in the back, two seats in the front, and you can see the geometrical complexity. So this is how the seats are captured as it is by the simulation software that we use, which is OpenFOAM. And yeah, so internal temperature was initially set to 300 Kelvin. Floor, ceiling, and sides were, however, set to 330 Kelvin. Inlet temperature or the temperature of the air that was thrown at the seats was 290 Kelvin, and a transient buoyant heat transfer solver was used along with a turbulence model. Right. So you can see different planes. So I've cut a plane where only one seat will be visible and a plane where two seats will be visible. You can see that the air conditioning system seems to be more efficient in terms of cooling the bottom side of this arrangement rather than the top side. So there needs to be more optimization done. And if you look at the velocity contours, you will again see a clear circulation of the air inside the system. Now moving on to a more realistic case. So okay, so this is the conclusion from the previous case study. You can see the streamlines and how the temperatures. You can see the streamlines on the top are hotter than the streamlines on the bottom. So, but we have successfully captured turbulence, buoyancy effects, heat transfer, and flow dynamics. Moving on to a more realistic air conditioning system that we performed for a Swiss company. Uh, Basically, they wanted us to develop a pipeline of CFD simulations, and using that data, they wanted to further utilize their pipeline of artificial intelligence to perform a multivariable constraint optimization problem. The optimization problem was supposed to fix the following parameters: duct size and shape optimization, inlet parameters optimization, heat exchanger optimization, gate angle optimization, and evaporator optimization. So I can't show much details about this case study, but whatever I can is on the screen. One thing that you will notice in the difference between these three data points is the change in the angle. You can see that the gate angle is different for the three different scenarios, and accordingly the flows have also changed a lot. Okay, in the first case the gates are completely open, so the flow is free to move, or the fluid is free to move all the way to the outlet in a very clean cut manner. In the third case, both the gates are completely choked, the flow cannot move much through the ducts and go into the actual car chamber, right? Talking about AI, this is something that we do as well. We develop AI systems if needed for efficient patent search or white space analysis with relevant statistics, and organizing and narrowing relevant proposals and ideas. And more directly on a technical side, we have the capacity or capability to develop dedicated artificial intelligence solvers or agents for prediction of experimental data. So most of these technologies I have shown are in their research phase, and when you are in research phase you develop a lot of data, right? So it's almost a crime to not use that data, and this data should be thrown at a machine learning algorithm, and we should be able to estimate some meaningful information out of this data, right? So to summarize all this, CFD in thermal management couples everything together, all the way from geometric complexity to the physics complexity. And this is the software that was responsible for generating all this set of beautiful case studies, validations, simulations. We totally use OpenFOAM because it is low cost. It's basically free of cost, open source, and but we do a lot of customization and add additional code on top of OpenFOAM. to make it more usable. And it is accurate because of intense validations. It has large users community of experts around the globe. It is scalable on cloud, so it is not limited by the core count. So if you have a 1,000 core cluster, you can as well launch it on 1,000 cores. You're not limited by 16 cores or 32 cores. It's customizable, which is very good, especially for these cutting edge areas of research. The existing CFD cores do not have the capability to be modified and customized by the user. So as well, but OpenFOAM provides you that opportunity to modify and tweak the code according to your requirement. And then state of the art visualization, as we have seen, all the photos and images and videos have come out of this state of the art visualizer called ParaView, which comes with OpenFOAM. Right, so how can Paanduv help in thermal management? We provide services wherein we can help you capture complex physics of your system, in developing industry specific custom solvers, coupling various physics into one single platform for easy usage. And this is the list of some of the upcoming webinars and some of the industries where we operate. We are working on the drone side of things, HVAC, turbo machinery, battery thermal management, water environment, aerospace and defense, and 3D printing is one of the big areas where our expertise lies when it comes to computational modeling. We also have an upcoming workshop on 23rd and 24th of April, where we'll be teaching industry and students, industry people and students like the CFD with OpenFOAM. We'll be teaching OpenFOAM all the way from scratch to intermediate to advanced level industry problem by the end of this workshop. And this time we are offering this workshop in 3 domains: thermal management, aerospace and defense, water and environmental. So if you are interested to learn OpenFOAM and ParaView, the registration link is in the YouTube description below. Okay, so this is where we are situated. We are situated in the northern part of India, near the foothills of Himalayas. Feel free to shoot an email to support@paanduv.com, and all our latest activity and updates are available on our LinkedIn page, which is Paanduv Applications. So you can just search Paanduv Applications and you will be able to follow us. And thank you very much, and looking forward to having some interactions for thermal management modeling, which so please feel free to write an email to support@paanduv.com. If you have any questions, I'll be happy to take them for the next few minutes. But you're always welcome to send all your inquiries to support@paanduv.com. AI plus CFD workshop, yes, this is under works, and we will send you out the details. If you can shoot an email to support@paanduv.com. Yes, we can simulate, all the modes of heat transfer, heating, radiation, conduction, radiation, convection, even the photocatalytic side of things. There are solvers for everything in OpenFOAM. Okay, please send your queries to support@paanduv.com, and I will end the webinar here, and see you again in the future webinars. Thank you.